Welcome back. So, in the previous lecture, we spent quite a bit of time in looking at the various aspects of how cancers can develop. And just to quickly recap, there are various intricate mechanisms by which growth and death are actually regulated. So, any of these processes can be in a state of imbalance, which can result to the development of cancers. So, we also looked at how there are two types of cancers. One is the benign cancers, which are very local and those are fairly easy to cure or not that difficult to cure, and the other one is the malignant cancers, which actually do what is known as metastasis. So, we looked at various mechanisms by which metastasis can occur and how they evade the immune system or recognition systems that we have in our body, and they can actually go to another part of the body to spread. And so, these are the cancers that are more difficult to cure and can be fatal. Now, we will look through some of the major strategies that are used to tackle cancer. A number of these strategies we have already discussed previously in the course, so I am not going to repeat the details. So, the first major class of drugs that act on cancers are the ones that act on nucleic acids. And so, we have already looked at previously that there are agents known as intercalating agents, which actually go and stack between DNA base pairs, and these can slip into the double helix and distort the structure. So, one of the examples that we looked at are these anthracycline based molecules, including doxorubicin, daunorubicin and so on. So, once this goes and intercalates, then the enzymes that are involved in the replication process and transcription process are actually inhibited. There are other agents which can act directly on nucleic acids, which are known as non-intercalating agents. So, the example that we looked at was camptothecin, and so these are actually sort of poisons. So, they act on topoisomerase 2, and inhibit it. Okay. And this can of course happen in the case of both normal cells as well as cancer cells. So, we have also looked at a number of DNA alkylating agents, and we have looked at in detail some of the mechanisms by which these act. And so, there are examples of these mustards which act on DNA by cross-linking it, and so here are the various classes of these drugs that are used. Okay. So, you can also have a prodrug concept which we have looked at previously. There are also DNA interactylating agents such as cisplatin and the improved versions of carboplatin and oxaliplatin, and these are very frequently used in the treatment of several cancers. Now, you could also have a prodrug of alkylating agents. So, we have looked at previously one example, but here we should look at another example, which is TH302. And as we discussed in the previous lectures, there is the center of tumors, or there are regions in tumors which have low oxygen tension, and this is due to the random blood vessel generation or the unregulated blood vessel generation, which leads to areas where there is less blood supply. As a result, there is less oxygen tension. And so, what we could do is we could exploit the low oxygen tension to develop prodrugs. So, here is an example of this molecule, which is a nitroimidazole structure here in the case of TH302, and there are a number of enzymes which act to reduce these nitro groups, or under hypoxic conditions this reduction of nitro group is actually promoted. Normally, this kind of process would be reversible. So, in the presence of oxygen, this would undergo oxidation and give you back the original molecule. However, under hypoxic conditions, this process is slow or does not occur. So, once an electron withdrawing group as the nitro group is now converted to a fairly electron donating group, this lone pair of molecules can then you can push arrows to kick out the active alkylating agent. So, this is one strategy that has been used to selectively deliver an alkylating agent to hypoxic cells. The other major mechanism by which we can target cancers is to inhibit biosynthesis. So, we have already looked at these cases previously, so I will not spend much time, but one could think of inhibiting thymidine kinase, and here below is an example of adenosine deaminase, which is very important. So, here the enzyme picks up H plus from a water molecule, activating it, which can then attack on this carbon here, and subsequent rearrangement kicks out ammonia, and gives you this amide over here. Okay. So, based on this mechanism, one could develop new inhibitors, and there are also DNA polymerase inhibitors, and these inhibitors generally work quite well. There are another major class of therapies that are used, which are known as hormone based therapies. So, here there are many cancers which are dependent on hormones. Okay. So, these hormones again, they can help in stimulating growth, and therefore, if the cancer is dependent on the hormone, one could use this mechanism to inhibit it. So, what we could do is then we could give a hormone which has an opposing effect, that is, it suppresses the growth of the tumor. Alternatively, the hormone antagonist can be used to block the action of the required hormone. So, these steroid hormones, which then combine with the intracellular receptors to form complexes known as nuclear transcription factors. So, by inhibiting these, we would be able to reduce the growth of the tumor. There is a large class of drugs which act on structural proteins. So, again, this is something that we have discussed previously. There are ways in which you can actually inhibit tubulin polymerization, or you can also inhibit depolymerization. Okay. So, here is the structure of epothelon, that is a depolymerization inhibitor. You could also have kinase inhibitors. As we discussed in detail, a number of the signaling processes are actually mediated by kinases, and these phosphorylate very specific amino acids in protein substrates. There are estimates which say that there are more than 500 different types of protein kinases, and a large amount of work is actually being done to study as well as inhibit these enzymes. We discussed in some detail about these enzymes known as matrix metalloproteases. So, these are the ones that are going to help with metastasis and angiogenesis, because they are going to help dissolve the matrix around the cancers. And these are cysteine proteases, and they also contain, they are zinc dependent enzymes, and there are few anti-cancer agents that are available that act against them. So, these MMPs are extremely destructive enzymes, and they are involved in the normal turnover and remodeling of the extracellular matrix and connective tissue. So, if one could inhibit it, this is one way to develop to prevent the cancer from growing. There is another class of enzymes which are known as histone deacetylases. So, histone acetylase is an enzyme that adds an acetyl group to a lysine residue. So, you have a lysine residue to which it can form an acetyl, it can add an acetyl group. Okay. So, these histone tails actually stick out from the chromatin structure. So, acetylation neutralizes the positive charge that would be normally associated with the lysine side chain. So, this would be in equilibrium with the plus. However, by acetylating it, what we have done is we have made the molecule neutral. So, therefore, this leads to a change in the DNA structure in terms of the packing, and it weakens the ionic interactions between the histones and the negatively charged sugar phosphate backbone, and this leads to what is known as a less compact structure. So, the more open structure allows for transcription factors to access the promoter region of the various genes. So, histone deacetylase on the other hand is an enzyme that removes this acetyl group. So, this leads to more compacting of the structure and prevents the transcription factor from accessing the promoter regions. So, this process causes gene silencing and also can lead to decreased DNA repair, resulting in an increased chance of cancer. So, histone deacetylase inhibitors are some things that can be used to effectively target cancers.